Okay, morning everyone. Let's get started. So first, please don't forget to submit your project choice and project proposal. I think it will be due today. Just let us know what's your project choice so that our TAs can make a note of the project type on the team member. Don't just send me an email or send TA an email. We request you to submit a PDF indicating your project choice and proposal. Okay. Any of you can submit. Yeah, but make sure your partner will submit. Otherwise, you get your points deducted. I mean, in terms of research, right? If you're doing Kaggle, you have to submit on your own because this is a solo project. Any other question? Okay, great. So let us review what I have discussed from last lecture. We talk about bagging, right? So bagging actually is a very straightforward and surprisingly simple approach. So basically, you can view that, okay, I'm going to independently train a collection of decision trees. I don't care about overfitting issues. I just let the tree to grow as large as possible. So how can we do that? So this is a pseudocode, right? So suppose you have a set of training examples with M examples. Then you're going to create big T decision trees. For each iteration, right, you're going to draw M samples uniformly with replacement, right? So this is something we emphasize that this is required because it's like, okay, I'm going to view my original training data as kind of like new data source. Every time I draw ID from that data source to get one sample, and next time I draw from the same data source again. So it is possible that one example can be drawn for twice or three times. That's the so-called uniformly with replacement, right? If the samples you draw has the same size as the original training data, then this redraw data set is called a bootstrap sample. And once we have constructed a bootstrap sample, we're gonna just feed them to our decision tree learning algorithm and using ID3 or CARD or whatever other decision tree algorithm you are in favor of, and then you get a decision tree. Right? So just to do this in parallel, because the tree construction actually does not depend on each other. It's not like AdaBoost, right? AdaBoost requires the weighted error from the previous round and to reweight the instances at current round, and then you can construct your weak classifier, right? So AdaBoost is sequential learning algorithm, but for bagging, you don't need to do any sequential. All this can be done in parallel. Right? So once you have got this big T trees, you can just doing vote for classification or doing average for regression, and that's it. So this is very, very simple. And then we discussed more rigorously why this seemingly simple or even naive approach can dramatically improve the prediction accuracy or performance in many, many scenarios, right? We introduced the so-called bias variance decomposition, right? So it's kind of a leverage our basic understanding of the definition for expectation and variance, right? So I'm not gonna like repeat the analysis procedure, but just give a very brief sketch. So if you want to look at what is your generalization error, so we can pick up any test example X star, right? Suppose this is your learned hypothesis H, right? So we're interested in under expectation from the data distribution, right? Meaning that, okay, you just keep joining test example X star from the data distribution D, and then look at the square difference or square error from a prediction. What will happen? Right? So we can leverage some kind of trick, right? So in this expected square error, we can plug in this expectation of our prediction from our learned hypothesis H and plus it, right? There's no change of the results because these terms are canceled. However, if you expand this square error, you will find difference, right? So it turns out that the cross term will become 0, and then the remaining term is a summation of this guy and this guy, right? From the definition, right? From the basic definition of statistical definition, we know the first term actually represents the bias term, meaning that if you take expectation of your prediction under your trained model, right? How much it will deviate from the ground truth table, right? And the second one is the variance. That means, okay, if you just keep drawing different test examples, you want to look at the prediction by a learned hypothesis like decision tree, what's the variance, right? So this actually represents a general trade-off between the model complexity and the performance, right? So if usually the larger the model, meaning that the more complex the model you have a smaller bias because it has so good capability to fit the training data, right? So that's why on average, we can believe that your prediction made by our learned decision tree, from being trained on data randomly sampled from data distribution, we're always close to the ground truth table because you fit the trained data so well, right? But those kind of like powerful models are often very sensitive to the change of the training set. Like take decision tree as an example, you know that when we just change the label of one example, the tree structure can have a large changes, right? In terms of structure, in terms of the selected attributes for the partition and so on. So that means like the variance is big, right? So some model might have a large bias, like the linear model we're going to discuss today, but because linear model is so stable, right? So if you change the data points quite a lot, it doesn't change the model very much. So it has small variance. So you can see that there's no like a perfect things, right? They can complex model tend to have a small bias but large variance, and this large variance arises from the nature of the model itself, right? Has nothing to do with the ground truth table. And simple models, though cannot fit data, train data super good, right? But it has a smaller variance. So overall, you don't know which one will get the best performance. And in practice, we are always trying to find out the best trade-off. Right? So if you look at decision tree, right, because decision tree tends to overfit, so it has a small bias but has a large variance. Then it comes to then the idea of the bagging comes to play, right? So now that my decision tree has small bias but suffer from large variance, so why not I independently train a bunch of decision trees, and then I use their average as my prediction. So know that for a set of independent, identically distributed random variables, if you take the average of them, you're going to largely reduce the variance, right? But their expectation won't change. So that would be very good, right? So if you take the average of set of independent decision trees, you can expect that by taking average, it won't change their bias. The bias is always small, but because you're taking average, you can significantly reduce the variance. So overall, you're going to have you're going to achieve smaller generalization error. So that's the whole idea and the justification for the bagging. Does it make sense? So just to quickly review what we have discussed. Any questions so far? Okay, great. So we have analyzed this regression case and showing this bias variance trade-off app. But it also have other types of bias variance trade-off for classification data. So if you're interested, you can take a look at this paper. This profound paper talking about 0-1 loss, meaning you're doing classification. It also exhibits the same thing. Okay. So although this balance variance trade-off can motivate us to like train a set of decision trees and take the average so that we can hope that we're gonna substantially reduce the variance. But this is constructed on the hypothesis that okay, our decision trees are really independent to each other, right? So let me write down. Let me write down something. So our justification comes from, okay, suppose I have a set of independent random variables, right? And if I take the average of those variables, right? I know that their expectation won't change, right? You take expectation of the average of set of IID random variables, the expectation doesn't change, that means your bias doesn't change. But your variance will be reduced significantly, right? So the variance will become 1 over n, right? Does it make sense? Right? This is like some basic calculation for variance, right? So you can imagine like the more independent decision trees you get, the more you can reduce this variance term. That means the more you can promote your generalization performance, right? But this is based upon our hypothesis that all those decision trees are independent to each other, right? Or have weak correlations, right? If those random variables x1 to xn are highly dependent on each other, right? Take an extreme case, suppose those trees are exactly the same. x1 and xn are actually the same variables. Will the average of them reduce any variance? No, it won't, right? So to effectively reduce variance, you must break as much dependency as possible for those set of decision trees. Does it make sense? If those trees are super correlated, right? Like take extreme case, suppose all those trees are the same, right? Their variance won't change if you take average, right? So that actually becomes the bottleneck in practice when we apply this bagging idea, right? So in the bagging case, right? So if some set of features are highly indicative or dominant all the other features, imagine how would you like resample the data set, reconstruct the bootstrap sample? It is always the case that those like top 20 features will be selected and split data set and then construct the tree. Then those tree structures will be highly similar to each other, right? And then even you have collected like say 20 such trees, because of the high correlations, you're actually not effectively reducing the variance. That means you won't efficiently or effectively improve the generalization performance. Does it make sense? That's the practical issue. So imagine in practice, your data set, you have 100 features, but it's always the case that the first 5 features are selected and then construct the tree. And as a consequence, those trees will be very similar to each other, right? In the first few levels. The more similar the tree structures are, the more correlated of their prediction, right? The more dependent of their prediction, and then as a result, you won't be able to, even you take the average of their prediction, you won't be able to significantly reduce their the variance, right? Does it make sense? Right? So then there comes a question, right? How can we avoid this situation, right? How can we, in practical bagging algorithm running, how can we try to make our trees, like if you use decision tree, right? How can we make sure our decision trees to be as less correlated as possible? Okay. So here comes our random forest idea. Okay. So random forest is actually the practically most popular version of bagging, right? I mean, in practice, people rarely just implement the pseudocode like, okay, just resample the data set and then train a decision trees independent. It's not like that. Instead, people will make efforts to make every tree to be dissimilar as different as possible to others. So this is called random forest. So let's see how do they achieve this point, right? How do we make our tree to be as different as possible to other trees? So the idea is very simple. So first, this general framework doesn't change. So in each iteration, we're gonna draw M samples to construct a bootstrap from the original data set. And then we're gonna modify our decision tree learning algorithm a little bit, which we call random tree learn. So what does random tree learn, right? So every time when we call this tree learning algorithm, imagine you're trying to leverage your ID3 algorithm to construct a tree, right? When we select the attribute and want to rank the attribute and pick the best one, right? Before that, we're not gonna go over every attribute from this current available attribute set A. Instead, we're gonna first random sample a very small subset of A, which we denote by G. Then we just look at the best feature in G, according to, say, information gain, gene index gain, whatever gain, right? To pick out the best attribute and then to split data. And next time when I call this algorithm recursively, right? And then to grow the tree in the lower level, I have another subset of attributes, right? And then I do this random subset selection again to reduce the range of attributes. And then in that smaller attribute, I'm gonna rank and pick up the best attribute. I just keep doing this. So you can imagine during the whole tree construction, every time you're gonna randomly leverage a subset of attributes out of the whole available attributes, and then construct a tree. So at every node construction, your selected attributes will be very different from other trees, right? In this way, you can dramatically reduce the likelihood that those trees are similar. Does it make sense? So that's the key idea. It's very, very simple. Just add one line of code before you calculate the information gain for every attribute. You're gonna first randomly sample a subset of attributes from A, and then just look at the attribute and calculate their information gain in that subset G. Any question? It depends on how you choose that. Depends on application. Like for example, one commonly used strategy is that, okay, I'm gonna take a set of ratio. Say I only take 20%, right? 0.2 times size of A, and I do random sample and then look at this small subset and the rank the attributes. Of course, you can set a fixed number of attributes. It's a flexible. Other comments or other questions? Okay, great. So now we have finished the discussion of ensemble learning, right? So here is our summary. Right? We talk about two ideas of ensemble learning. One is called boosting, one is called bagging, right? So boosting is a sequential learning algorithm. You're trying to base upon the achievement your previous classifiers has made, and then retrain the classifier to, correct the big mistakes your previous version had made, and try to make it better, right? So it's called boosting. And the most commonly used approach is called ADA boost. I remember we're training a collection of weak classifiers one by one. Right? Every time we're gonna calculate the error of the current weak classifier and reweight every training instance. On those weighted training instances, so we retrain our classifier. We hope that by doing this, our classifier will correctly classify those examples that are incorrectly predicted by the previous classifier and improving it. And finally, we're going to assemble those weak classifiers all together through a linear combination. This is ADA boost. Another approach is bagging. Right? Bagging is different from ADA boost in that we're not doing like sequential learning. Each tree learning or each base classifier learning is not dependent on previous classifiers. So that means bagging can be done in parallel, right? But the concern about bagging is that you should take enough randomness to ensure the learned decision trees or learned base classifiers are not correlated to each other. Otherwise, you cannot effectively reduce the variance of the average of the prediction and then improve the generalization error. Okay, so far, any questions? Great. So hopefully those, from algorithm perspective, those methods are straightforward to implement. And we have released our homework too today, and but we do have enough time to do that because the deadline will be 1 week after the fall break. So we do have enough time to take a look, but you can start looking at it and do something if you feel comfortable. Okay, so next. We're going to discuss so next we're going to start discussing another collection of models. Oops. Which we call linear models. Okay. I don't know what happens to the projector. Okay, starts working. It's like, okay. So So this is a class of seemingly simple but very, very important machine learning models. Right? So don't get confused about the so-called linear. So linear models here just means a linear structure inside the model. Later we'll see that by injecting some kind of tricks, linear models can do very, very powerful nonlinear stuff. Right? So it actually forms the basis of neural networks and support vector machines. Those are like super powerful nonlinear classifiers or regressors. Right? Okay, so let us step back a little bit and look at the bigger picture, right? So so far we have talked about supervised learning, the framework, right? And we have introduced the basic concepts about instances, instance space, labels, label space, hypothesis, and hypothesis space. Remember, supervised learning is always a searching procedure, right? So you want to use a collection of labeled training data to guide a search procedure over some hypothesis space. You want to find out a hypothesis which you believe is best approximation to the ground truth function. And that's it. That is supervised learning. And I hope that your learned hypothesis H will generalize well, meaning that given some new examples other than training data, it can perform well. Right? So we have talked about several specific learners, like decision trees, AdaBoost, bagging, and so on. And through our discussion, we introduced several important concepts like overfitting or pack learnability. Right? So everyone comfortable? Any question? Okay. So then we're going to discuss the linear models, right? We'll talk about the general notation and the definition for linear classifiers. Before we talk about the expressivity, before we talk about how can we learn linear models, we want to look at the expressivity of linear models, right? We want to look at, okay, what kind of functions can linear classifier represent? What kind of functions cannot, right? And then from an algorithm perspective, we'll start with the so-called least square method for regression. Okay, so first, what are linear classifiers, right? So we start with some kind of specific example, right? So here is a collection of labeled instances on a plane, right? So obviously we have two labels, positive and negative. You can view those red triangles as positive instances and blue circles as negative samples, right? So suppose this is our training set, and we have to separate the blue circles from the red triangles. Now ask, which will be the best classifier? The first classifier will be just a curve, right? A vivid curve which can exactly separate every red triangle from the blue circles. The question is, will curve A perform well? I mean, in terms of generalization. And the second choice is that, okay, I'm gonna draw a rough line, which kind of cross the border or interface between these red triangles and the blue circles, right? But obviously, this is kind of like quite rough, and it's not as delicate as fine grain as the curve A, right? Okay, the question again is which classifier is line B or curve A do you believe will work better in generalization? Why line B? Okay, that's a good point. Any other suggestion or comment? Okay, looks like everyone favors B. Okay, yeah. Yeah, that's really good, right? So we know that curve A obviously have zero training error, right? If you use curve A to classify every training instances, it will be perfect. It is perfect, right? It's 100% accuracy, right? But if you use line B to do the classification, you see the training error won't be 100%. Actually, you can immediately identify several wrongly classified examples surrounding the interface, right? Like this guy, like this guy, like this guy, right? But why do we still favor B? Because B is more robust, right? So A is more obvious, it's more complex, it's more fine-grained, it's more vivid, it kind of like adapt to every possible case in the training set, right? But as we discussed previously, if your training set itself has some problematic, right? Has some noises, has some issues, and have some wrong labels. Actually, it can mislead curve A, right? For example, if some samples happen to be mislabeled in the training set, right? Then during the prediction phase, right? Suppose I got a blue circle here and the red triangle here. and the curve A will make mistakes. Right? Why? Because it was misled by the wrongly labeled or by noise, by corrupted labels like here and like here, to make it so curved, right? But if we use line B, we see that it's kind of like quite robust to this noise corruption, right? That's why it shows such a rigid interface, so that it is much more immune to those noises. And once you classify this guy and classify this guy, it works great. Similar argument can apply to the regression case. Remember, regression is trying to predict some real value labels, right? So suppose this is a set of data points we're given. This might come from the read of some like millimeters or some gauge, some whatever, right? And you can definitely use some kind of like more complex polynomials, right, to perfectly fit every data points like curve A, and then your training square error will be 0. Right? But another more robust choice will be some line like line B, right? So it looks like line B will kind of like largely misfit this point. But imagine, why does this point deviates from other points so much? In practice, this doesn't really mean good things, right? It usually means that, okay, this point as an outlier, it's kind of corrupted by some noises. That's why it's kind of like seem abnormally be far away from all the other trained data points. And in this case, if you still train a very expressive model to perfectly fit these outliers, that usually doesn't mean good things, right? Because you're influenced, you're misguided by these outliers, which is highly likely to be corrupted by some noises, right? That's why we want to return to this more robust linear regression, which is line B, right? So that in our prediction phase, if you want to really predict some input, the label for some input here, right? We know the ground truth should be close to other data points. That means close to this line. So your error will be small, right? But if you use curve A, because curve A is totally distorted or misled by these outliers at this surrounding this position, right? So you can view like the prediction for this input for this at this location will have large error. Does it make sense? Right. So because of simplicity, right, linear regression can be more immune to possible noises and the perturbation of the data samples, so it can make smaller errors on new points. Okay, so that's one major motivation of a class to do to learn linear classifiers or linear regression model. But what are linear classifiers? So what are linear regression? So here we give some like definition. In general, suppose our training input or testing input is represented by an n-dimensional vector x, and our output is a label is either -1 or 1. So here we just consider binary classification, but this is very easy to generalize to multi-class classifiers. Linear classifiers are also called linear threshold units. They're going to classify an example x using a weak vector w. So w has the same dimension of the feature vector x, and one bias parameter b. So this b is a number, it's not a vector. And then linear classifier use this rule to generate the label. So we're going to calculate the dot product between the weight vector w and feature vector x plus this bias term, then look at the sign. And of course, if the sign is 1, then prediction is 1. If the sign is -1, meaning your score w transpose x plus b is negative, then we're going to predict the label as -1. Okay. So b is called bias term. So this is our classification rule for linear classifiers. Almost all the linear classifiers follow this rule and this definition. So any question regarding the definition? Everyone feels comfortable, right? So we see that linear classifiers only need n plus 1 parameters, right? N is the number of features or the dimensional feature vector. And n plus 1 meaning that we have also to include a bias parameter B, right? In addition to this weight vector W. Right? So any linear classifier is only determined by a weight vector W and bias parameter B. Right? And the rule is simple. You use this linear function, which is dot product between W and the input feature vector X plus bias parameter B as your score, and look at the sign of the score to make the prediction. Okay. So now we want to look at what kind of geometry can be reflected by linear classifier. Suppose we have a set of positive examples and negative examples. So if we look at the prediction rule of our linear classifier, so we're taking a look at the sign of this score function, right? This score function is B bias parameter plus W1 x1 plus W2 x2, right? So obviously there will be a boundary, right? From the geometry we have learned, right? There will be a boundary, right? The boundary corresponds to the equation that the score is 0, right? And of course, when all the points on one side, on the right-hand side of this boundary will be positive and classified as positive, and on the other side, those points will be classified as negative, right? So this is the geometry meaning of a linear classifier. So you can imagine like every linear classifier tries to set up a classification boundary, which is either line in two-dimensional space or plane in three-dimensional space or hyperplane in a higher dimensional space. And in this way, they kind of like partition all the instances in the instance space into two half spaces, right? One half space is on one side of boundary, and the other is on the other side. And all the examples in the same half space will be classified as either positive or negative. Does it make sense? Okay. So another important insight is that this classification boundary is orthogonal to this weight vector, right? Meaning W1, W2, this is vector, right? This vector, the angle between this vector, weight vector, and the boundary is 90 degrees. As to why is this the case, I'll leave it as an exercise for you. Just recall what you have learned from, I don't know, grade 7 or grade 8. You'll be able to show that. Okay, the third point. If you're doing a classifier, right, we actually do not care about the magnitude of the score, right? We'll only care about the sign. So meaning that we can just multiply any positive factor with those model parameters B, W1, W2. It doesn't change the boundary at all, and doesn't change the direction of the weight vector, so it doesn't change the classifier. Does it make sense? Right? We multiply W1, W2, and B by 0.1, the classifier doesn't change. By 10 doesn't change. By 10 to minus 3 doesn't change. By 1 million doesn't change. Why? Because you don't change the position of the boundary. You don't change the classification results for every instance in this whole space. So that means your classifier doesn't change. Does it make sense? Right? So this is a very, very important insight. That means like one classifier, one linear classifier can have infinitely many representations in terms of model parameters, right? For any, like in this case, the parameters include three, right? B, W1, W2, right? And for one single triplet B, W1, W2, you multiply them by arbitrary positive factor, they correspond to exactly the same classifier. So keep this in mind, because later when we discuss the support vector machines, and this is a very, very important insight to help us simplify the learning objective of support vector machines. Any questions so far? Okay. Okay, so when we extend to n-dimensional space, right? The linear classifier represents a hyperplane that separates the space into the half spaces. This is just as we mentioned, right? In the two-dimensional space, which is a plane, your linear classifier specify a line which separate this plane into two half planes, right? In three-dimensional space, this equation is represented by a plane, right? It separates the whole three-dimensional space into two half spaces. And you can extend this idea into high dimensional space, into arbitrary dimensional spaces. And then this classification boundary actually serves as so-called hyperplane, and which splits the spaces into half spaces. Right? Okay. So oftentimes we feel like we explicitly write out the weight vector W and B is kind of like a tedious, right? And so people also invent a simplified notation, right? So we can view like, okay, we're going to rewrite our feature vector X as inserting a constant 1 into X. I got my new feature representation, X prime. So remember, X prime is nothing different from X, only except that I'm going to insert one constant number, 1. And then what's the benefit? The benefit is that, okay, I'm going to fold the corresponding bias term into the weight vector to get a new weight vector. Right? So you can see B corresponds to 1, right? And the original weight vector W corresponds to our original feature vector X, right? Then we can simplify the prediction as just the dot product between W prime and X prime, and then take the sign. Right? Does it make sense? Right? Because you know, B is folded in W prime, right? The constant 1 is folded in W prime. So you do this dot product, you still get W transpose X plus B. It's the same thing, but we have some notational sugar, right? To help us avoid writing out an additional symbol. Right? But remember, when we use this simplified notations, this bias parameter B is still there. You can view it like, okay, we add an additional constant feature 1 in our data. Any question regarding the notation? Okay. Okay. So after introduction of the definition of linear classifiers, right? Next, we're going to talk about next several weeks actually. We're going to talk about several classical classifier learning algorithm. We'll start with the simplest one. It's called perceptron. Okay. You'll see that it's an error-driven online learning algorithm. It's a lazy learner in that it will only update model parameters when it misclassifies some example. Right? You keep doing this until you can correctly classify every training example. Right? And then we're going to introduce the support vector machines, which is a very powerful linear classifier. You see that support vector machine is motivated by the result of computational learning theory, and then it invents some kind of cost function which can try to trade off between the training error and the generalization error, which is reflected as the margin term, as we discuss later. Right? And then we're going to introduce two probabilistic linear classifier. One is called naive Bayes classifier. The other is called logistic regression. Okay. So those are the linear classifiers we would like to discuss. But then we'll also talk about linear regression. So what does linear regression mean? We just want linear models to predict real value outputs. Right? So you have to take any statistical class before you might have heard this term before, or even know what does it mean for at least the mean square estimation. But later we'll discuss a little bit more from the not a little bit more from the algorithm perspective. We're going to introduce what is the effective training for linear least mean square loss, right? And for convenience, when we do a binary linear classifier, right, we'll assume the label is either +1, -1, right? Or if you're dealing with more categories, then we can define the labels as like 1, 2, 3, 4, 5, right? But throughout our discussion, we'll mainly focus on binary classification. That's why we always choose +1, -1. Okay. Okay. So next, let's discuss the expressivity of linear classifiers. So we would like to know how much flexibility does the linear classifier have, right? After all, when we look at the definition, it seems it's kind of like a quite restricted classifier, right? Because assume everything is represented by a linear score, right? So we will use Boolean function as an example to explain how expressive linear classifiers are, right? So we talk about which Boolean functions linear classifiers can represent, which are not, right? Okay, so the conclusion is linear classifiers are an expressive hypothesis class. And if we look at the Boolean functions, you will see many Boolean functions are linearly separable. However, not all of them are linear separable. Right? So from this case, right, if we think back to consider decision trees, linear classifiers actually are less expressive than decision trees. Why? Why are linear classifiers less expressive than decision trees? Can decision trees classify any Boolean function? Is it possible? Yes, right? Remember when we discussed about introduced the concept called overfitting, we discussed about that issue, right? If you can give all possible examples to decision tree, let it grow as deep as possible, as large as possible. Eventually, it's going to represent every possible instance in this Boolean function, right? So that means for any Boolean function, the decision trees can perfectly fit it. In other words, it can perfectly represent it. But we'll see, linear classifiers can only represent a small subset of Boolean functions. That's why would say like linear classifiers are less expressive than decision trees. But let's look at several examples where that can be well represented by linear classifiers, right? So first, we would like to look at the conjunction rules, right? So suppose your Boolean function has this form. So your function output or label is a conjunction of these three Boolean variables, x1, x2, x3. I want to ask how this conjunction function is represented by a linear classifier. How can we construct a linear classifier which is equivalent to this conjunction function? Yes, exactly, right? So we need to look at the property of this conjunction rule, right? So what's the conjunction rule? It is only one when all variables are ones, right? any variable not being 1, like being 0, the conjunction will give 0 or false. Right? That's the conjunction rule, right? And because those you know, x1, x2, x3 are just Boolean variables, that means they can either choose 0 or 1. So that means if the output y is 1, x1, x2, x3 must all be 1. That means their summation must be at least 3, right? In other words, the conjunction of x1, x2, x3 is equivalent to saying y is 1 if and only if the summation of x1 to 3 are at least 3, right? Otherwise, your y must be 0, right? So in this way, we can construct a linear classifier. Remember, right? This is our score function, right? x1 plus x2 plus x3 minus 3, right? So just to take a look at the sign of this score function. And if you look at the table which represents this conjunction function, you see that for all the cases that y is 0, the sign of the score function will be 0 as well, right? Because that means there will be at least one variable, input variable is 0, then the summation of the 3 variables subtracted by 3 must be negative, right? So sign is 0, right? So there is only one case you're going to have a positive, that is all x1, x2, x3 are 1s. So the sign of this guy will be positive. So in this way, we kind of like construct an equivalent linear classifier to represent this conjunction rule, right? So now I want to ask if I made some kind of small modification. I have a conjunction of x1, x2, and the negation of x3. Can we represent this guy by a linear classifier? Can we? I saw some of you are nodding. Negative weight. Yeah, but yeah, you're right, right? But how do you flip it? That's okay, right? But imagine like x3 actually takes the value either 1 or 0, right? It's not taking value as 1 or minus 1, right? So we need a little bit transformation. Add 1 to what? And then yeah, you're right, but you don't explain why, right? Yeah. So actually, the value of negation of x3 actually have been pointed by you and you, right? Can be represented by 1 minus x3, right? It's not minus x3 because x3 is either 1 or 0. Its negation is either 1 or 0 as well, right? But its negation can be represented by 1 minus x3, right? Does it make sense? Right? So that basically means like, okay, I want a conjunction of x1, x2, and negation of x3 to be true or to be 1. It basically means, okay, their summation x1, x2 plus the negation of x3 must be at least 3, right? So negation of x3 is represented by 1 minus x3. So we get here, right here, right? So this is equivalent to saying that y is 1 if and only if x1 plus x2 plus 1 minus x3 no less than 3, right? And that's it. Any question? Okay, great. And then you do some kind of like rearrange and merging, right? You immediately get our classifier equivalent to this new conjunction rule. That is x1 plus x2 minus x3 no less than 2. And that's it. Okay. And then we can consider what if we replace the conjunction by disjunctions? Suppose oops. Suppose I replace conjunction by disjunction. Let me write it more clear. Right, this is my new Boolean function. How can we represent this disjunction function by linear classifiers? Any thought? So what's the disjunction rule? What? Yeah, you're hitting the key, right? But let's first look at what's the disjunction rule. As long as one variable is one, then the function value is one, right? It doesn't need all variables to be one, right? It just need at least one variable to be one. And it is zero if and only if all variables are zero, right? And from that, we can say, okay, if we want to make our function value to be one, that basically means the summation of all three variables to be no less than one, right? No less than one, no, that one just means, okay, at least one variable must be one, right? If it doesn't meet this, right? That means x1 plus x2 plus x3 is zero. And of course, the disjunction will give you zero. And then we can construct our linear classifier, right? It's simply, our score function is simply x1 plus x2 plus x3 minus 1, right? You can construct a table for disjunction and then contrast it to this score function and check their equivalence. I will leave it as an exercise for you. Okay, so next, let us look at a little bit more non-trivial examples, right? Which is called M of n rules or M of n functions. So what is M of n functions, right? So we're assuming there is a fixed set of n variables, right, which is your input variables. And y is true if and only if at least m of them are true. All the other variables are ignored. So suppose there are three Boolean variables, x1, x2, x3, right? So 2 of 3 rules means that as long as there are 2 variables out of these 3 variables are true, then the output will be true. The question is, how can we represent this 2 of 3 rules by a linear classifier? How? Any thought? Yeah, exactly right. That's it. Like surprisingly simple, right? So we want them at least m of them to be true, right? To check that, we just need to make sure there's summation to be at least 2, right? That's it. Any question? Okay. However, not every Boolean function is that simple to linear classifiers. There does exist cases which are not linearly separable, right? And one important formula of this type of function is called parity. So as long as your Boolean function reflects parity, it can be showing that you won't able to find out one line or one linear boundary to classify positive examples from negative examples. Okay. So what does parity mean? It's like something like this. So you have a positive examples in this way along this direction, and you have a negative examples along that direction. The distribution of the examples are kind of across, and then one can show that you won't be able to draw a line to separate two classes, no matter how you draw it. You can try that, right? You can try this one, right? It won't work, right? And try this one, and try this one. And you can try all of them. You see that you will never be able to find a line which can well separate all the positive examples from all the negative examples. Okay. So if we go back to the Boolean function, right? A very well-known parity function is called XOR. XOR can be represented in this way, right? Y equals to, X1 conjunction, disjunction X2, negation of X1, conjunction, disjunction, negation X2, and then do the conjunction, right? So that basically means like X1, X2, only when they are different, the XOR value will be 1, right? If they are the same, like 1, 1, then XOR value will be 0, or 0, 0, value will be 0. Right? This is XOR, right? If you try to place the instances and the labels for XOR function in a plane, you will see exactly this kind of same layout. That's why you can't draw any line to separate out positive and negative examples. But in addition to XOR, there are many other non-trivial Boolean functions like this guy is now linear in 4 variables as well. So actually this has been proved by a pioneer in artificial intelligence called Marvin Minsky, who just passed away like, I think last year, right? That is kind of like when perceptron becomes very popular and becomes a hot research area. People back up to 60 years ago, people even believe that, okay, you're going to build up perceptron machine, which can be really intelligent, right? And then Marvin Minsky used this simple example to show the limitation of perceptron. Like you can even not separate out these XOR examples. How could you imagine your perceptron as a simple linear classifier can do intelligent things, right, as human beings, right? So that kind of like push the artificial intelligence to the first winter. And then in 1980s, with the popularity of neural networks, and then the artificial intelligence kind of resurged, and then it was go down, and now it's going up. Okay, although linear classifier itself even cannot handle this XOR case, do we have any remedies to address this issue? Here we're going to introduce a very effective trick, which is called feature mapping. So look at this one-dimensional points, right? So each point can be represented by a single feature, right? That is the position, right? Obviously, you cannot draw any line to separate out the positive examples and negative examples, right? Definitely you cannot, right? That means it is not linearly separable by our training examples. And then the question is, how can we make them linearly separable, right? How can we make our linear classifier to be able to handle them? The idea is as follows. Now that in the original feature space, I cannot do anything with my linear classifier. Why not I construct some additional features? Right? For example, in the original space, every example is represented by its location X, right? Now I append X squared to X to form a two-dimensional feature representation for every data point. So you can imagine with this new feature transformation, every point is now located in the two-dimensional space, right? Now let us say in the two-dimensional space, what will happen? You see that these points becomes linearly separable. Right? This ability is attributed to the newly augmented features called X squared. Right? With this new feature augmentation, it's very easy to find a hyperplane or lane, which kind of like a line, which kind of like well separate the positive examples from negative examples. So this is called feature mapping. Right? It depends how you smartly construct additional features based upon the existing feature representation. Right? If you can make it smartly, and then you can address this nonlinear separability issue. Okay, so now this will be left as an exercise for you guys, right? How would you use the feature transformation of the idea to make X4 in 2 dimensions linearly separable in new space? Think about that, right? Maybe this method doesn't work, right? I don't know. I have a little exercise for you, right? X4 function itself, right, is not linearly separable because it exhibits parity. Okay? You can show that, and by joining them, by joining the positions in the original feature space, right? But now, if you could smartly construct an augmented feature, and then lift the representation of every instance in a higher dimensional space, then probably you can overcome this issue. You can still find a hyperplane or linear classifier that will separate positive and negative examples. And think about that. That has already included in our homework too. Right? Okay. The next few things about representation of linear classifiers is that in practice, right, training data is in many cases not like exactly linear separable. Right? As we mentioned, right, there are always some cases like blurring examples or corrupted examples, which make the interface of the positive and negative examples kind of like hard to differentiate, right? But I want to avoid using too flexible and too expressive models so that we can avoid overfitting, right? So in that case, we just seek for almost linearly separable data, meaning that as long as we can draw a linear classifier which can separate out most positive examples from most negative examples, then we feel good, then feel satisfactory, right? So then the question is, how much noise shall we allow for? Right? In other words, how much misclassification can we allow for our linear models? So this also relates to the support vector machines we're gonna discuss later. You see that on some extreme case, you want to draw some kind of line that minimize this training error, but that will kind of reduce the margin of linear classifier and then reduce the hurt to the generalization capability. On the other hand, like if you try to increase the margin to be as large as possible, and then there will be a lot of examples like break into the margin, so make your training error worse, and which will also hurt the generalization performance. And support vector machines are just trying to find a trade-off. Right? We'll discuss about that later. Okay. So now we have finished our discussion about linear classifier representations. Many functions are linear, as we have seen. So basically, we can view linear classifier as okay, acceptable hypothesis class, right? And it's also a good guess for a hypothesis space. However, we need to realize many functions are not linear. Like even for Boolean functions, there are type of like XOR non-trivial Boolean functions are not linear, meaning that no matter how many training examples you give linear classifiers, it won't perfectly classify every examples because of the limitation of its expressivity, right? But there are ways of making them linear in a high-dimensional feature space. This is called feature mapping. Okay? If you can smartly construct new features for this to represent each data instances, and that means really you have to lift the feature representation in a higher dimensional space. That would be a lot easier to find a linear classifier well or better separate positive examples from negative examples. Any questions so far? Okay. So the last question regarding our today's lecture is, why do we need a bias term in the definition of linear classifier? So it looks like the position or the direction of our classifying boundary is solely dependent on the weight vector W1, W2. Remember, W1, W2 is orthogonal to the boundary, right? But why do we need a bias term? Any thought? So what if we remove a bias term? Why do you think it will be bias concentrated? Mm-hmm. Oh yeah, okay. This is yeah, that makes sense from this perspective, right? But we can think about, okay, if we get rid of bias term B, where will this classification boundary will be? So that means, okay, my classification boundary will always be W1 plus X1, W2, X2 equals to 0, right? This is my new classification boundary, right? What happened to this boundary? Yes, right? Because of the bias term, vanishing of the bias term, this boundary will always cross 0, right? Cross the origin, right? Look like this, right? So that means, remember, the W1, W2 can only govern the direction of this hyperplane, right? That means you change W1, W2, you can rotate this hyperplane, but you cannot move it away. It's kind of locked in the sense that it will always pass through this origin, which is not favorable. Consider like, okay, I have a set of data points surrounding this origin, right? And no matter how you rotate your hyperplane, you won't be able to well separate the positive examples from negative examples, right? We do need some additional flexibility such that I can move this boundary out of the origin. That's the effect of the bias term. So the bias term is important, although it's just a number, right? But it kind of like enhance the flexibility of the classifying boundary, allow it to be everywhere, right? To be any position in this whole instance space rather than fixed to be passing through the original the origin point. Okay, so now we finish our discussion about the definition and the basic properties of linear classifiers. On Thursday, we're going to start talking about the least mean square learning for linear regression models. Okay, see you on Thursday.